portion, the OpenHPCA, and UCX Development Working Group. The contributors that either stole slides from or got information are listed here. A lot of these are folks who are on the OpenHPCA team, and most of the slides, or at least the content of the slides of the OpenHPCA slides that I'll be showing, was generated by the entire team. So what I've done is taken what the entire team did, put it out in some slides so that we could look at it. There, you guys have to go to the wiki and read it all yourself. So here's sort of an agenda. First of all, I'm going to talk about some potential futures, or at least things that I think we might be able to look at for UCF topics. Then I'll give the OpenHPCA mission statement. Then talk about some potential benchmarks that the OpenHPCA team has generated. These are just proposed benchmarks. There's a whole collection of them, as well as the very last one, which is a library that does metrics, telemetry, and analytics that would be basically owned and released through UCF. So here's some potential future topics. Now, a caveat is none of these have been approved by the UCF board. So these are just ideas of things that we might want to look at in, going down and continuing to generate things for the UCF Consortium itself. The first one is an open source common memory/packet tracing facility and/or API. Now, the reason I put this as a need is because Los Alamos and other national labs and other large computing facilities many times cannot release their codes. So, and we change machines or we change vendors seemingly reasonably often. So a nice thing for us to be able to have would be one of these tracing capabilities where I can send a trace of an application to a vendor and say, here, I may not be able to send you the entire application, but I can at least send you some memory traces and potentially some network traffic traces. From this, they could enter this into their simulator and do a virtual rebuild of the memory traffic and the network traffic, which are, some of the problems that we run into. Now, for this packet and tracing facility or the API, I'm not requesting and not asking for an entire system simulator. There are a bunch of those. They take forever to run, and if you really want to run them, you stuff them in hardware. So this has to be lightweight, and for the switch or for the network API or tracing facility, I want to be able to trace in and out of the NIC and in and out of the switch. Yes, that's a rather interesting call, but it is something that we're interested in because it allows us to do a potential fault analysis. The other thing is we can run analytics on it. We can analyze and verify security postures within the switch or the NIC, and we can look for cases where we actually have data or packet corruption. Los Alamos is unfortunately notorious for destroying machines and/or destroying components because of the altitude. We end up getting an enormous number of faults or errors that will bring our machines down, and that's a very unpleasant thing, is to watch an entire computer room, or at least the application you are running on an entire computer room, die, and because it ended up getting a single event upset in memory that was uncorrectable, or that can be memory in anything. It could be memory in the switch. It could be memory in the NIC. It could be memory on the host. So the other thing we want to be able to do with the network and the memory one is the memory tracer. We would like to be able to analyze switch designs, not just us doing switch design analysis, but giving some of these traces and some of the analytics that we've done back to the switch and the NIC designers and say, here's what we've found. Here are ways that you might be able to make your system more efficient for traffic that looks like the following. we did this in about 2012 for a system it was very useful because it allowed us to relay out the topology of the network based on certain applications because we'd already analyzed what the traffic patterns looked like. And the algorithmic analysis, I want to see where the packets have been, who and what they have touched, so I can generate basic traffic graphs. And then, of course, like I said, you can give a user could actually run these traces and give them to potential NIC, switch, or topology system designers, which is what we did quite some time ago. We wanted to be able to dynamically reset up what the routing path looked like based on what our algorithms were doing. Now, for the memory, this is also a need for us because of, like I said, we have cases where we cannot send our applications, and there are other people who do that. The petroleum business has a real hard time sending out their applications because their bread and butter and their money has nothing to do with security. It has to do with money, and they don't a lot of times like to send those out. But sending out some kind of trace is more amenable to their existence as it is ours. We're interested in NUMA issues. Why would we be interested in NUMA issues? Well, we're looking at, as I said, looking at for future architectures. We do not necessarily know that we will have a flat memory space. The chances are not good that we will have a completely flat memory space. We might have a CPU complex itself that has both HBM and DDR. That's a possibility. It could have HBM only, it could have DDR only. Then we're looking at GPUs where there's some kind of memory, pick your whatever you like. And then a combination of those two, where I've got CPUs with different types of memory integrated with, in the same system as a GPU with its kind of memory. And then I now bring in a SmartNIC. The SmartNIC has memory of some type, whether this is an FPGA kind of SmartNIC or it's a SmartNIC that has ARM processors and uses DDR or whatever memory type is used in the SmartNIC. Now I want to be able to trace where all of this goes, because as the complexity of these systems grow, being able to trace and analyze where you might run into faults or where there may be some inherent shortcomings in the design, God forbid, of whatever piece of hardware you're using, it's quite useful to be able to do full fault analysis and go back and find out where exactly things failed for you. And if we have memory traces, we can give the memory traces to CPU designers, memory controller designers, and SmartNIC designers, as I said earlier. We can give them the memory traces that they can run then through their simulators and give them if you will, a broader database of information to look at how well their controller works with things and applications that we run. Prime example there would be what happens if I had a really strange scatter-gather capability and I wanted, and it's just killing the memory subsystem. I want to be able to give that to someone who's doing a memory controller design and say, here's an example of a problem, like pick GUPS, for instance. I could give them a memory trace of GUPS both locally and remotely through the network and say, this is a simulation of a fairly complicated degenerate case of scatter-gather. And that way you can freely give it away. Again, the memory tracing thing we can use for fault analysis, analytics and security. One of the things that we worry about is with the complexity of the systems coming up, we're starting to worry about any potential security flaw or potential security opening. So that's the open source memory packet tracing facility API. Now we see this, LANL sees this at least, as a very ripe place for lots of collaboration. We can abstract away as much as required so that vendors don't have to open source everything of how their subsystems work, but having an API that you can hide some of that underneath would still make it easier for us, because we can run it with what we need And then if the vendor really needs to use it and doesn't want to tell all of their secrets, which we understand, they would at least have a common infrastructure that we could do CPUs, GPUs, smart NICs, computational storage devices, etc. So the next thing that I've been thinking about is a UCF branded network performance and exercising benchmarks. Yes, there are zillions of network performance benchmarks out there. One of the problems is, and we should decide what we want to do. So it has to be network vendor agnostic, which says that it won't necessarily take into consideration all of the bells and whistles that a vendor might want to put in there. But at least from the API point of view, if you think of OpenSHMEM, that's what we did with OpenSHMEM. We came up with a generalized API that's still growing, and vendors are allowed to put underneath that API the stuff that they feel will make their particular device shine. So of all the capabilities that exist out there, do we want to start with one and adapt and adopt it by putting an underlying either UCX or OpenSnappy interface? Because the whole idea here is to try to get some of what we're doing in UCF out there to the user so that they can use it, and it shows what the capabilities of the smart NICs are when it comes to running things like network benchmarks, etc. And as part of this, one of the things I've really been thinking about is I want to be able to put in there either optional calls or otherwise analytics and the tracing options that I mentioned earlier. That way it allows vendors to optimize it, do whatever they want to, but by default they have to run the baseline just like they have to do with any of the top 500 blah kind of packages that people run. Must run the baseline. Then if you want to optimize it, that's fine, but you have to at least run the baseline to give everybody on equal footing. One of the reasons for this is we want to make sure going forward in the machines that we're purchasing for LANL, we want to make sure that all of the networking vendors, smart NIC and otherwise, we want to make sure that there is a sort of an interesting common benchmark so that we can get to ground truth as to what are the fastest networks that we can buy for our systems, not just buy it because some vendor said this is good. We actually want to be able to start comparing honestly what network vendors offer to us. One of the things that we've just started looking at is a summer student to at least start roaming through what some of the capabilities are and how we might hide or how we might put OpenSnappy underneath it. Next, again, not approved by the board. We'll have to, beg for forgiveness at the board and see if they say anything. So one of the other things that LANL has got into recently is computational storage, and this is a requirement for LANL. One of the reasons is, and I'll go into a lot more about this in the OpenSnappy talk, but one of the reasons that computational storage is required for LANL is we are starting to look at how can we compute on some of the data that we need to compute in situ, not post-process the data, but compute it while we do it, as well as not just do analytics. So for UCF and OpenSnappy and UCX, this is sort of like a natural outgrowth. It's almost a no-brainer. And if you look at if you remember the UCX diagram, I/O is the middle tower, if you will, in that collection. So LANL's been pushing this for probably 6 months, maybe a year, and this will be more in the OpenSnappy talk. Well, that was wonky. Can you guys see that? The JAMF stuff? Oh, awesome. That's good. I'll have to try to read around it. So, which is a pain in the behind. Anyway, so the other thing that we're looking at is, hang on, one of the other things that we're looking at is we started talking with many vendors in the computational storage side of the world and and they're actually getting quite interested in it. One of the reasons, of course, is because Lanel buys a whole buttload of disks, and storage devices. So one of the things that we're doing, and you'll see it in the Open Snappy talk, is that we are actually getting a growing storage vendor and standards engagement on this process. So one of the things that we're looking at is 1 or 2 killer apps that encompass all or most of the above things that we've discussed, come up with some very interesting workflows to show potential improvements or weaknesses in the way that we're trying to attack open benchmarks. And the Open Snappy talk, I will give you 2 examples of potential test cases that we are actually working on right now. I'm interested in generating an analytics library, which will run on SmartNICs and run underneath Open Snappy, that will be produced by the OpenHPCA team, because the OpenHPCA team is going to need all of these analytics in order to actually run their benchmarks. Otherwise, we'll be able to do a benchmark, but it will be absolutely meaningless because we won't gain any knowledge from it. I'm also interested in trying to not necessarily broaden UCF engagements to just give a lot more money, but one of the ideas here is to increase the engagement of other accelerator and processor vendors. We've got quite a few now, but when it comes to CSD devices and things like that, we are just starting to scratch the surface in people who have computational storage devices or general computational storage capabilities. So we started talking to all of the vendors that Lanel is talking to for some of our programs, and we are letting all of them know about Open Snappy and Open UCF. I'm very interested in trying to figure out how we can get an externally available test bed or 2 where we can start running some tests at scale. Now, one thing that might be possible is if people can run their test cases on smaller systems, we might be able to move them to systems that are available to Lanel in the open. What we will have to make sure that we have all of the same capability. Another thing I'm going to bring up to the board, and get yelled at, I'm sure, but that's okay. I'm very interested in what about an in-kind buy-in? Let's say we have a vendor, and the vendor may or may not, they may have reasons, or someone may have reasons where they can't pay what it takes to become a card-carrying member. What about if they were to donate an enormous amount of hardware or a reasonable amount of hardware for a test bed that the entire team could use? I realize that's a difficult thing, but it's at least a start. One of the other things, and this is the last in the future topics, we need to figure out how we're going to release some of the software that is being generated by the UCF Consortium. Now, because we now release it on GitHub, or we do all that other stuff, but when it's on GitHub, I'm not sure that it has a good branding, that it basically came from the UCF umbrella. And that's something that I've been interested in. And one of the things we want to make sure is we want to learn everything we can from what we don't think went right with OFA. So it's not to rain on OFA's parade. It's to say that what we want to be able to do is make sure that we never go down the path that OFA ended up going down. And being one of the original founders of OFA, I can actually say that. Come on. There we go. Excellent. Oh, back up one. Boy, this is slow. Okay, come on. OpenHPCA. The reason I decided to talk about OpenHPCA for a little bit is, Pasha, give me a hint when I'm almost done. OpenHPCA, not a lot of people know about. It's only about 6 months old. We've started having the meetings and have a pretty good turnout. But the mission statement for OpenHPCA is provide a comprehensive set of useful, operative term there, useful, benchmarks to evaluate the overall compute resource performance in the presence of in-network or in-fabric acceleration computing technologies. Yeah, okay. So one of the things that OpenHPCA really is we want to come up with applications in which we will integrate and exploit other technologies under the UCF umbrella. OpenSnappy, some of the UCC stuff, UCX certainly. And we want to be able to release these as fully integrated where people can load them, run them, and test them. And so you can think of HPCA now as your application slash user space problems, where what we do in the HPCA domain is we take the technologies that have been generated in the other portions of UCF and we integrate them into benchmarks. And then we release the benchmarks and we certify and validate the benchmarks so that other people can load them, run them, and get the benefits that we think will be able to be gotten from OpenSnappy and some of the other portions underneath UCF. And so in some of the slides that I'm going to present, the interesting thing is the OpenSnappy team and the OpenHPCA team do not have an enormous number of overlapping members, which is kind of good because it did not prejudice, if you will, anything that we came up with in the benchmarks or the proposed benchmarks. And there was a lot of stuff that when we came up with, it was certainly a large overlap. So this is where from you guys, the developers, the library developers, your input is required and requested, and we would like, we don't want to come out with something that's impossible to start with, but we do want to come out with something that's going to exercise whatever technology you're releasing in your libraries. So having the developers help us rank order what our proposed benchmarks are would be awesome. See if it'll go to the next page. Okay. So I'll go through these relatively quickly. I don't know how much time I have left. So storage by use in network computing is for load balancing is quite obvious. It's grayed out because we have we know some people who are working in areas like this. Key value stores, obviously. On-node compute resources, it frees them up. We know about that. I'll talk a little bit about that in the OpenSnappy talk. And well, when the LANO runs the problem that they're looking at, one of the things we will be looking at is improvement in OS noise reduction. So one of the other things that's really interesting is trying to use OpenSnappy and some of the things under UCF to minimize and speed up the capabilities of monitoring, system monitoring, both application and system. So LANO uses things like Splunk, which we can't play with Splunk because it's sort of off on its own. But we do have a lot of open source monitoring tools that we use, and we've started talking, at least internally to Los Alamos, if they would consider looking at UCF-izing some of what we currently use to see how much information they could get from the hardware rather than have to do all the software probes. And we're sort of looking at trying to see if we can get a summer intern to look at this, because a lot of what we use is open source, and it's very it's easier for the students to play with. So you might want to consider a lot of this sort of edge computing. The things in green I'll get to later. So in network mathematics, it's kind of a no-duh. Using the network as a coprocessor, which we already do. Some of the questions are, what is the impact on the data size if I move this stuff to SmartNICs or computational resources? How does this work? I mean, what's the determination of the proper mix? Can I model the proper mix? How do I know when to offload and when to just leave it on the host? Because if the cost to do the data move, and if I'm only doing light computation, this is something that Brody did some initial work on, trying to analyze by looking at some applications. When would it be useful to actually offload and give enough work to the NIC the SmartNIC to make it worthwhile, make it truly a computational resource. Data compression, data reduction, Lanel is already doing that. We're doing it with a little small company called Identicom. It's used in this case for storage, for one of our storage problems. What we've done is we've put the erasure code and some other things actually in their SmartNIC. Their SmartNIC is basically FPGA based. So programming FPGAs is, you know, something you do on the weekends, but it's we put in the erasure code there because by default Lanel has to run multiple levels of erasure code to protect our data from any large number of disk failures or storage failures. Matrix transpose, matrix multiplication, all of the typical sort of tensor arithmetic and convolution is quite useful. Convolution and correlation are used quite heavily in many fields, but the petroleum business is one of them. One of the things that I've been working with, and we've been talking about with Graham for quite some time, is to be able to do a full FFT inside the network, which is kind of an interesting problem. FFTs have very broad applications. Locality, this is pretty obvious. Bring the computation closer to the data, or the data closer to the computation, which is the whole idea behind SmartNICs. This is not, you know, some kind of brain, you know, positive thing. But early pre-staging of the data. Now, one of the things that we're interested in is, can we push the data out to the SmartNICs or whatever before we start working on it, even the computational storage devices? Can we push not only the data, but what we want to do out there? So a lot of this has been done in the past. A lot of this is not brand new. Most everybody knows about burst buffer technology. And if you go back 3 or 4 decades, you can look this up for, you know, for all the younger crowd. You might want to look up Jez 2, Jez 3, or RACF. All of this stuff was done probably 30 years ago. And old Cray systems used to have something called an SSD, where you could literally pre-stage everything you wanted to out to the SSD, then operate on it from within a program. Lanel came up with something called LibHIO, which they used for the burst buffer so we could stage out to some kind of memory space before we started working on it. Berkeley, Argonne, Oak Ridge, and Livermore have done similar things. And just one of the things is pay attention to Megan's talk on some of the work that she and Pasha have done in the PMEM space. And of course, move tasks to networks. Everybody's already doing that anyway. It's just we're working on it. Machine learning, hot topic, growing applicability, huge opportunities. So one of the big questions is, if we're going to do this, and this is where I'd like a lot of input from you guys. One of the things that we looked at was adopting ML-Perf benchmarks to work with OpenSnappy. Now, that's a non-trivial undertaking, but one that I think is quite doable, and we could get quick turnaround. So Grossman and Dinan have been working on doing ML issues and published some papers on ML issues with OpenSHMEM. That at least gives us a potential space to work in. You know, enabling PyTorch, TensorFlow, all that good stuff, using OpenSnappy and SmartNICs. Even Lanel is finally, you know, fallen prey to looking at ML and AI for some of our mission applications, strictly because if there's any way that we can shorten the time it takes for us to run some of our compute problems, it helps. Because, you know, I think I've told you guys before, we have some problems that run, you know, 6 to 9 months on half of our machines, on half of one of our large machines. And anytime you can take that from 7 months or more down to less than a month, life is more pleasant. People are happier that you haven't had to use the entire machine for over half a year. So what would an API look like if we wanted to do, you know, ML inference assist in network computing? So I'm going to move on. Multi-threading is pretty obvious. The one thing that is kind of interesting is with the advent of the SmartNICs, and almost all of them have a reasonable amount of memory on it. If you look at it now, the SmartNIC is yet another memory space, which is what I discussed in the tracing. If you look at n number of gigabytes per NIC, let's say 16 to 32 gigabytes per SmartNIC, and you have 1,000 or so of those, now you have terabytes of additional memory that you can play with and you also have to watch. One of the things, of course, that we're looking at, seeing how all of us are into scientific types of computing, is halo exchange. Nowadays, this is very network intensive and done basically in the network. Sandia has been looking at how they might do halo exchange in the fabric itself. Parallel programming, all this is pretty obvious. We have done a bunch of work on PGAS, and that was done by Brody and Jack Snyder, Brody Williams and Jack Snyder. We published that, and it's in the repository if anybody's interested. It was done with OpenHPCA and MPI, and we did that with an application of ours, as well as some, I'll talk about it in the Open Snappy thing, but also some Department of Defense applications. And one of the things I said, Brody studied, what's the opportunity cost? When do you actually do this? Because if you just do it willy-nilly, it's probably not going to be that great. And the rest of this is, how do you handle non-contiguous data? And if it's in the network, or if it's in the network cards itself, it might be easier to deal with and let the smart NICs do a bunch of the work for OpenMPI or for MPI, data packing, etc., because they already have the data. And if they have space on the NIC, it's quite useful to use that. Security. This is really interesting because I don't see a lot of people doing a lot of this work in the security with smart NICs. So, in-network traffic analysis, detection for abnormal traffic behavior, which is, quite useful. Abnormal communications between applications. One of the things that we were interested in was, if I put things in containers and I try to do something bad, can I ensure that I can't do anything bad? So that's something that's of great interest to people who run more secure computing. And if you put this out in the edge, you can certainly try to detect attacks on the systems at the edge. Yes, encryption currently does exist in almost all of the smart NICs. It certainly does in the Bluefields and in the Stingrays that we have. But the problem is, I want to be able to load my own application. That's not that I don't trust anybody. Never mind. So anyway, I'd like to be able to load my own specific algorithms. Virtualization offloads. This is not so much HPC centric, but it's extremely important from a vendor point of view, because there are probably more people using cloud and all of this than there are using HPC. So we wanted to make sure that we at least included these capabilities in one of our, in at least an analysis for a benchmark, because there are a lot more hyperscalers, et cetera, than there are necessarily large HPC vendors. So here's the last slide. Well, next to last slide. So this is the library, the telemetry, analytics, and metrics slide that I'm interested in seeing that we could start to develop anytime we wanted to. And you can see what are the things some of the things I'm trying to look for, the things we want to be able to put. These will be integrated into whatever applications, our benchmarks that we run, so that we can collect this information. And when we run it against a model, we save the information. When we run it against a real app, we save the information. We build a database, which I've done in the past, of signatures, so that we can then do comparative analysis between what we thought and what we actually ended up getting. And here's my slide. Here's the Consortium, SmartNIC, all the links. So I think that's it. I stole that from Pasha.